My dear students, welcome back to our channel. In this video, I will be explaining the BCA first semester subject Mathematical Foundation of Computer Science, MFCS, as prescribed by Osmania University and other universities of Telangana. We will go through the important questions and answers one by one. Let's begin with a quick revision. Unit 1 first important short question is: define conjunction and disjunction with truth table. Conjunction and disjunction with truth table. In logic, we combine two statements using special words like and or. 1. Conjunction, PQ. Conjunction means and. The final statement is true only when both P and Q are true. Example: P. I study. Q. I pass. PQ. I study and I pass. If I don't study or don't pass, the statement becomes false. Truth table. PQ. TTT. TFF. FTF. FFF. 2. Disjunction, PQ. Disjunction means or. The final statement is true if at least one of P or Q is true. Example: P. I drink tea. Q. I drink coffee. PQ. I drink tea or coffee. If I drink any one, the statement is true. Truth table. PQ. TTT. TFT. FTT. FFF. Easy trick. And all true. Or one true. Next important short question is: 2. Define inverse, converse, and contrapositive with examples. Inverse, converse, and contrapositive. Consider a statement of the form: PQ. Meaning if P happens, then Q happens. Example: P. It rains. Q. The ground becomes wet. Original: if it rains, then the ground becomes wet. 1. Converse. Converse means reversing the order of P and Q. So it becomes QP. Example: if the ground is wet, then it rains. Memory trick: converse is equal to change the order. 2. Inverse. Inverse means adding not to both P and Q without changing order. So it becomes PQ. Example: if it does not rain, then the ground is not wet. Memory trick: inverse is equal to not P, not Q. 3. Contrapositive. Contrapositive means flip and add not. So it becomes QP. Example: if the ground is not wet, then it did not rain. Memory trick: contrapositive is equal to converse plus not. Contrapositive is always logically equivalent to the original statement. Next important short question is: 3. Define quantifier and universal quantifier. Quantifier and universal quantifier. In logic, a quantifier is a symbol that tells us how many elements in a set satisfy a statement. It helps us talk about all, some, or none of the elements without writing each one separately. There are mainly two types. 1. Universal quantifier means for all. 2. Existential quantifier means there exists. Here we focus on the universal quantifier. Universal quantifier. The symbol is read as for all or for every. It tells us that a statement is true for every element in a particular set. Example: x plus 0 is equal to x. Meaning, for every natural number x, adding 0 gives the same number. Another example: x superscript to greater than or equal to 0. Meaning, for every real number, the square is non-negative. Easy memory trick. Is equal to all. Turn the symbol sideways and it looks like an AA for all. This makes it very easy to remember. Next important short question is 4. Define tautology and contradiction. Tautology and contradiction. In logic, some statements are always true and some are always false. These special types are called tautology and contradiction. 1. Tautology. A tautology is a statement that is always true, no matter what truth values P and Q have. Example: PP, meaning P or not P. This is always true because either a statement is true or its opposite is true. Another example: PQ, QP is also always true. Easy memory trick. Tautology is equal to totally true. 2. Contradiction. A contradiction is a statement that is always false for every case. Example: PP, meaning P and not P. A statement and its opposite cannot be true at the same time. Another example: false true is never possible for both sides. Easy memory trick. Contradiction is equal to cannot happen. These to help us check if logical expressions are valid or impossible. Next important short question is 5. Construct the truth table for the implication PQ. Truth table for implication PQ. In logic, implication means if P, then Q. It is written as PQ. Here, P is a condition and Q is the result. Example: P, I study. Q, I pass the exam. PQ, if I study, then I pass. Important rule, easy to remember. Implication is false only in one case. When P is true and Q is false. In all other cases, implication is true. Think of it like a promise. If you promise if I study, I will pass. And you study but don't pass, promise is broken false. All other cases are true. Truth table of PQ. PQ, TTT, TFF, FTT, FFT. Memory trick. TF is equal to false. Everything else is equal to true. This is the easiest way to remember implication. Next unit 1. Long questions. First important long question is: construct the truth table for PQ, PR, QR. Truth table for PQ, PR, QR. The given expression has three variables, P, Q, and R. To build the truth table, we must consider all possible combinations of these three variables. Since each variable can be true, T, or false, F, we get 8 rows, to superscript 3 is equal to 8. The expression is PQ, PR, QR. This means PQ true only when both P and Q are true. PR true when P is false but R is true. QR true when Q and R are true. Finally, we take OR of all three parts. Remember, OR becomes true if any one part is true. Step-by-step truth table. PQR, PQ, PPR, QR, PQ, PR, QR. Easy explanation. Let's understand why the final column is true or false. When any of the three parts becomes true, PQ, PR, QR, the final answer becomes true. If none of them is true, the final expression becomes false. Memory trick. Think of the expression as saying, if P and Q are together, or P is false and R helps, or Q and R support each other, result is true. So you just check whether any pair helps. If at least one pair works, result is true. Final result. The expression is true in 4 rows and false in 4 rows. Next important long question is 2. What is logical equivalence? Write the logical equivalence statements for the laws used in mathematical logic. Logical equivalence. In logic, two statements are logically equivalent if they always have the same truth value, no matter what values their variables take. We write this as PQ, meaning P is equivalent to Q. Example. Consider the statements. 1. PQ, if P, then Q. 2. PQ, not P or Q. No matter what P and Q are, these two statements always have the same truth values. So, PQ is an example of logical equivalence. Laws of logical equivalence. Here are the important laws used in mathematical logic. 1. Identity laws. PFP. PTP. Meaning, or with false or and with true doesn't change the statement. 2. Domination laws. PTT. PFF. Meaning, or with true is always true, and with false is always false. 3. Idempotent laws. PPP. PPP. Meaning, repeating the same statement doesn't change it. 4. Double negation law. PT. Meaning, not of not is the original statement. 5. Commutative laws. PQQP. PQQP. Meaning, the order doesn't matter for and or. 6. Associative laws. PQRPQR. PQRPQR. Meaning, grouping doesn't matter for and or. 7. Distributive laws. PQRPQPR. PQRPQPR. Meaning, and distributes over or and or distributes over and. 8. De Morgan's laws. PQPQ. PQPQ. Meaning, not of and becomes or of nots, and vice versa. 9. Implication law. PQPQ. Meaning, if P then Q is same as not P or Q. Easy memory trick. And multiply truth values. Or add truth values. Not flip the value. These laws help us simplify logical expressions and check if two statements are equivalent. Next important long question is 3. Prove that for every integer x, if x is odd then x superscript 2 is odd. Prove for every integer x, if x is odd then x superscript 2 is odd. We are asked to prove that the square of an odd number is always odd. Let's do it step by step. Step 1. Recall the definition of odd numbers. An integer x is odd if it can be written as x is equal to 2k plus 1, where k is any integer, 0, plus or minus 1, plus or minus 2. Example. 3 is equal to 2 times 1 plus 1 odd. 7 is equal to 2 times 3 plus 1 odd. Step 2. Write x superscript 2 in terms of k. If x is equal to 2k plus 1, then x2 is equal to 2k plus 1, 2. Now expand the square. x2 is equal to 2k plus 1, 2k plus 1 is equal to 4k2 plus 4k plus 1. Step 3. Factor out 2. x2 is equal to 4k2 plus 4k plus 1 is equal to 2, 2k2 plus 2k plus 1. Let's call m is equal to 2k superscript 2 plus 2k, which is an integer because k is an integer. x2 is equal to 2m plus 1. Step 4. Conclude that x superscript 2 is odd. The formula 2m plus 1 is the definition of an odd number. Hence, x superscript 2 is odd. Step 5. Example to understand easily. Take x is equal to 5, odd number. x2 is equal to 5, 2 is equal to 25. 25 can be written as 2 times 12 plus 1 odd. Works perfectly. Take x is equal to 7, odd number. x2 is equal to 7, 2 is equal to 49 is equal to 2 times 24 plus 1 odd. Step 6, easy memory trick. Odd number is equal to 2k plus 1. Square it 4k superscript 2 plus 4k plus 1 factor to 2 plus 1 still odd. Rule to remember. Square of odd is equal to always odd. This method works for every integer, positive or negative. Next important long question is 4. Using Venn diagrams, illustrate the laws of union and intersection of sets. Using Venn diagrams to illustrate the laws of union and intersection of sets. In set theory, we often combine sets using union and intersection. Venn diagrams are a visual way to understand these operations. 1. Union of sets A-B. Definition. The union of two sets A and B is the set of all elements that are in A, in B, or in both. Example. A is equal to 1, 2, 3. B is equal to 3, 4, 5. AB is equal to 1, 2, 3, 4, 5. Venn diagram. Draw two overlapping circles, one for A, one for B. Shade all parts of A and B, both circles. Memory trick. Union is equal to U for everything together. 2. Intersection of sets AB. Definition. The intersection of A and B is the set of elements that are common to both A and B. Example. A is equal to 1, 2, 3. B is equal to 3, 4, 5. AB is equal to 3. Venn diagram. Draw the same two overlapping circles. Shade only the overlapping part where A and B meet. Memory trick. Intersection is equal to common part. 3. Laws of union and intersection illustrated. Commutative law. AB is equal to BA. AB is equal to BA. Venn diagram, switching circles does not change the shaded area. Associative law. AB, C is equal to A, BC. AB, C is equal to A, BC. Venn diagram, grouping of circles does not change the combined area. Distributive law. A, BC is equal to AB, AC. A, BC is equal to AB, AC. Venn diagram helps visualize how shading distributes over union and intersection. Easy memory tips for exams. Union is equal to all shaded. Intersection is equal to only overlap shaded. Think of overlapping circles to remember which part to shade. Venn diagrams make it super easy to check set laws visually and avoid mistakes in exams. Next important long question is 5. State and prove the division algorithm. Division algorithm. The division algorithm is a basic result in number theory. It explains how any integer can be divided by a positive integer to get a quotient and a remainder. Statement of division algorithm. Let A and B be integers with B0. Then there exist unique integers Q, quotient, and R, remainder, such that A is equal to BQ plus R where 0 less than or equal to RB. A is equal to dividend. B is equal to divisor. Q is equal to quotient. R is equal to remainder. Example. Divide 17 by 5. 17 divided by 5 equals 3, remainder 2. A is equal to 17, B is equal to 5. Q is equal to 3, R is equal to 2. Check 17 is equal to 5 times 3 plus 2. Proof of division algorithm, step by step. Step 1. Consider the set S. Let S is equal to ABK KZ, ABK greater than or equal to 0. This is the set of all non-negative numbers obtained by subtracting multiples of B from A. Step 2. Well-ordering principle. Since S is a set of non-negative integers, it has a smallest element, call it R. Let R is equal to A, B Q for some integer Q. Step 3. Show 0 less than or equal to RB. By definition, R greater than or equal to 0. If R greater than or equal to B, then RB is equal to A, B, Q plus 1 greater than or equal to 0, which is smaller than R. But R is the smallest element of S contradiction. So RB. Step 4. Conclude. We have A is equal to BQ plus R with 0 less than or equal to RB. This proves the existence of Q and R. The uniqueness can also be shown using a similar argument. Memory trick for exams. Divide, get quotient and remainder. Formula: A is equal to BQ plus R. Remainder rule: 0 less than or equal to RB. Example: 23 divided by 7Q is equal to 3, R is equal to 2. 23 is equal to 7 times 3 plus 2.